In the last video, I talked to you about the two axioms that constitute axiomatic design, the information axiom, which we will not discuss in this part of our presentation on axiomatic design, and then the independence axiom, which we are going to demonstrate mathematically in this video. So I'll show you the mathematics and then give you a couple of simple examples so you'll get an idea of how this is used. And I've also put on our SharePoint site some additional information about axiomatic design that is not found in our text. So we talked about customer attributes and functional requirements and design parameters and process variables. Let's see how we express particularly the design, functional requirements, and design parameters in mathematical form, and how we check for this independence that appears to be so important in axiomatic design. Remember that first axiom says the ideal design would be one in which, if we change a design parameter, only the functional requirement associated with that design parameter would be impacted. None of the other functional requirements would be impacted. So let's see how we express that mathematically. Well, we're going to set up a design matrix, and that matrix is going to have m rows and n columns. And the rows are going to be aligned with our functional requirements. So our customers have told us what it is they want, and now we've determined how to cast those wants and needs in terms of functions that need to be met, functional requirements. And the next thing we're going to do is we're going to decide how we're going to embed those functional requirements in an actual physical way through our design parameters. So M will be the functional requirements, and N will be the number of design parameters required. So our design matrix will be M rows and N columns. So you'll see here I have this equation written out in matrix form. FR is a vector made up of M customer or functional requirements, and A is the design matrix made up of M by N rows, and then we have a vector of our design parameters that will be made up of N design parameters. So the question that this matrix asks us to determine is, if I change design parameter 1, how will that impact functional requirement 1? And will it impact functional requirement 2? And if so, then I haven't met that independence requirement that I'm looking for. So the way we say that mathematically is we hold everything else constant and we change only one thing at a time. So we look at this functional requirement 1, take the partial derivative of that requirement with respect to the first design parameter, and see what happens to the remaining functional requirements. Well, when a design is uncoupled, which is the ideal design, we'll end up with a design matrix that looks like the one shown here, where we only end up with terms on the diagonal of that matrix. And so the way to look at this is like this. So for functional requirement 1, we take the first partial derivative of FR1 with respect to DP1, multiply it by DP1, that design parameter, and then you see with the next design parameter, I have a 0 in this matrix, so it's 0 times DP2 plus 0 times DP3 plus 0 times DPN, and so forth. So the only functional requirement that will be impacted by changing DP1 will be functional requirement 1, and that's what I want. And if we continue to go through the exploration of how changing these design parameters will affect our functional requirements, when we have these uncoupled designs, we'll end up with this diagonal that basically says if I change DP1, it's not going to impact functional requirement 2, functional requirement 3, and so forth. So this is an uncoupled design. And we get this nice mathematical representation because we can see by looking at it that we do not have a coupled situation. So this is the ideal design. We change one design parameter and it affects only the functional requirement it's associated with. Now the second kind of situation we can have is where we can change a design parameter and it affects multiple functional requirements, but not all of them. And if we even rearrange the functional requirements and the design parameters mathematically, we can get what's called either an upper triangular or lower triangular matrix with the other part of the matrix being 0. So here we have what's called an upper triangular matrix, where we basically have the matrix in the upper part looking like a triangle with elements that constitute, say, a full first row and a full last column, and then proceed along the diagonal with everything else being 0. And so the way you would read this particular situation is like this. If I change design parameter 1, that is, it's in the design to impact functional requirement 1, so I actually want that. Design parameter 2, if I change that, in this case, it's going to impact functional requirement 1. And if I change design parameter n, it's going to impact functional requirement 1 as well. So this isn't the ideal situation. It's called a decoupled design. We can look at the problem a little differently if we want. I'll show you an example of how that happens in just a second. And sometimes if we even recast the problem statement, we'll come up with solutions that will get rid of this coupling of our design parameters. But this is a decoupled design. And frankly, it's very difficult to come up with uncoupled designs. To come up with a decoupled design where changing design parameters will affect multiple functional requirements, but not all of them, is better than a design that we call coupled, in which we change a design parameter and it affects all the other functional requirements, and that happens with every design parameter in our system. And in that situation, you see we get a full matrix of these elements. Now, it's important to point out that you may not have numerical values in this matrix. You can, if you can cast your problem in terms of mathematical qualities or quantities that are going to impact your functional requirements, but it's not necessary to tell if you have a coupled, decoupled, or uncoupled design. All you need to be able to do is determine how a design parameter will actually affect a functional requirement without attaching actual numerical values to those things, or without actually coming up with a function. So we'll end up getting a lot of people will actually just put X's in this matrix where there are occurrences of a change in a functional requirement with a design parameter. So those are the different types of situations that will occur with axiomatic design. Uncoupled, which is ideal. Decoupled, which is not the perfect design, but it's a better design than one in which a change in design parameters affects all other functions. So let's look at some corollaries that go along with axiomatic design that will help improve, in particular, those decoupled designs, or even coupled designs that are difficult to decouple. If we have functional requirements that are coupled, we want to try to separate the parts of the functional requirement or aspects of a solution. And sometimes breaking design parameters into separate physical parts isn't necessary. We don't have to have a separate mechanical component for each functional requirement. Sometimes it's possible to combine functional requirements that are met individually with a single mechanical component. We want to try to integrate design features into a single functional part if the functional requirements can be independently satisfied in the proposed solution. So in other words, if the design doesn't get too unwieldy by specifying distinct design parameters for each functional requirement, or more specifically, if the design doesn't get too unwieldy by specifying distinct mechanical components for each functional requirement, then we actually want to do that. But again, it's not always necessary, as that first corollary states. We know this from previous design courses or from experience, where standardized or interchangeable parts will help make a better design, and it helps make more consistent functional requirements and constraints. It also minimizes or helps to minimize the information content in a design. We want to try to use symmetry to our advantage. If we can use symmetry to assemble components and make the assembly easier. Again, remember, information content is measured by the amount of instructions involved in um, the fabrication or even operation of a design. So we want to try to use symmetry to our advantage, if we will. So those are corollaries that will help our uncoupled and decoupled designs become stronger in their ability to meet functional requirements with fewer mechanical components. Here's an example of a coupled design, and we've all seen these. This is just a hot and cold water faucet, and you turn the hot water on and cold water on, and you keep adjusting the rotation or the angular rotation, angular position of those faucets in order to get the right mix of temperature and flow rate that you want. And so what we're controlling in this case is flow rate and temperature. And here's our upper level hierarchy. It's a water faucet. We could actually say, if we're looking at functions instead of the actual device, we might say something like control the flow rate and temperature of a liquid. So the mechanical components that make this up are our hot water handle, our cold water handle, and then we have a hot water supply and a cold water supply, and we allow each of those supplies to come through different lines into the spout, and of course we control the flow rate and water temperature by combining those appropriately with these rotations. Well, the rotation I'm representing with this omega H and omega C. So the design matrix looks like this. Again, our functional requirement is to control temperature and flow rate. And so I look at the partial derivative of temperature with respect to how I change the angular orientation of the hot water faucet. And then I also look at the partial derivative of temperature with how changing the angular orientation of the cold water faucet impacts those things. And so I can see right away that this is going to be a coupled design because I get a full matrix here. There are two things that control the design parameters are the angular orientation of these two faucets, and temperature and water flow rate are the outputs. And then if I change the hot water faucet or hot water knob, it's going to impact the degree to which I have to control the cold water faucet. So this is definitely a coupled design. So let's look at another one where we can actually get some decoupling. We still have our water faucet, but let's change the way we look at this problem. Let's look at it as a mixing problem instead of a flow rate and temperature problem. And so we want to control the mixing ratio, which we've called R, and the flow rate we're going to control with A. So we're still trying to control temperature and flow rate, but we're looking at mixing and controlling the area of the faucet. And so now what you'll see is that if I change the flow rate, that's not going to impact, if I change the mixing ratio, that's not going to impact the temperature as a function of cross-sectional area. And then if I look at how I'm controlling flow rate, if I change the mixing ratio, that's not going to impact the flow rate, but changing the cross-sectional area of the faucet will. So what I end up with here is an uncoupled design where mixing ratio and area are resulting in a decoupled design that will give me control over temperature and flow rate. So here we have the same design parameter structure, but now we're looking at a mixing space and controlling the area of the spout as our design components or specifications that will give us this uncoupled design. And I still have a hot water supply line and a cold water supply line, but I'm using those in a mixing space. And as I understand the way this faucet actually works, there's also controls here on how much hot water is coming from the supply line and how much is coming from the cold water supply line. But the reason I like this as an example is it shows you how if you recast the problem, it is possible sometimes to take a design that's fully coupled and get one that's uncoupled. So you see how these design matrices can be used to help you determine if you have an uncoupled, decoupled, or coupled design. So in summary, you want to determine your functional requirements based on your customer attributes. You want to determine the design parameters that you're going to need to meet your functional requirements. And you're going to look at using this design matrix and your design parameters to determine if you have a decoupled, uncoupled, or coupled design. And if you have a coupled design, you or a decoupled design, either one of those two situations, you want to look at those corollaries that we went through using symmetry and minimizing the number of custom components, using interchangeable parts, those kinds of things to reduce the information content without compromising the functional requirements of the design. And then, again, those can be powerful things to remember in trying to get a decoupled design or reduce the complexity of a coupled design. So that's our presentation on axiomatic design. One final note that's important, and I don't want to leave this out, because the way this works ideally is when you're going through the functional decomposition, you will come up with a layer of functional requirements, select the design parameters for that layer, and then go to the next layer. So where we had that hierarchical functional decomposition, layer by layer by layer, the ideal way to do that is specify all your design parameters for one layer at a time and go back and forth until you get to the level of detail where you're down to the very specifics of the design. And that's called zigzagging, and it's an important part of the axiomatic design procedures. So break down the design into its functional requirements one layer at a time, specify your design parameters, and then go on to the next layer. So that's our very brief introduction to axiomatic design. I have other examples if you'd like to see those and want to apply those to your design, just let me know.